Assalamu alaikum, everyone. Welcome back to our discussion on laminar flame speed. So in the last class, we looked at the trends of laminar flame speed, essentially in terms of how it varies if we change the equivalence ratio, we change the fuel chemistry in terms of looking at different fuels, or looking at different fuel oxidizer mixtures with different reactivities and effect of pressure, and also initial temperature. Here we were looking at the effect of each of these parameters individually, and we came up with some conclusions in the sense of how it behaves, by saying that the laminar flame speed behaves very much like adiabatic flame temperature when only equivalence ratio is changed, right? And we see that behavior here. And then we looked at fuel chemistry, and we said the faster the chemistry, the higher the laminar flame speed is, and so on and so forth. We spoke about the fact that majority of the hydrocarbon fuels have very similar laminar flame speed in a rather narrow range. However, hydrogen has a much higher uh, flame speed, and that's because of its fast chemistry, but also the fact that it has a very high diffusion coefficient. Apart from hydrogen, acetylene is another fuel which has high laminar flame speed. Now, in terms of pressure, we said that laminar flame speed decreases with pressure, and it roughly follows, or it's sort of inversely proportional to square root of P, as shown here in this um, figure, which is showing the effect of laminar flame speed for methane airframes at different pressures, right? And then lastly, we said that the laminar flame speed increases very significantly with increase in initial temperature T naught, right? And as you can see here, as the initial temperature increases, the initial part where you start increasing the temperature, there the laminar flame speed increases approximately as T naught square, or is directly proportional to T naught square, and then later on it follows. The growth slows down a little bit, but overall it's very sensitive to the initial temperature. Okay. Now what we will do in today's class is to simply solve a problem related to calculation of laminar flame speed, the unburned gas velocity, and trying to understand the direction of flame propagation based on these numbers. Okay, so this is a rather simplistic numerical problem, but it's a very practically relevant problem, which can give us ideas about blow-off, flashback, and the other instabilities that can occur. So in this particular case, we're talking about a cylindrical tube burner. Okay, it has a 5 centimeter diameter. So let's just draw a simple tube burner with a diameter of 5 centimeter. Now we're supplying it with a premixed mixture of butane and air. So what is coming in here is a mixture of butane. Butane is C4H10 and air, right? So this is the mixture that we are providing it. Now the volumetric flow rate of the mixture is given as 15.5 liter per minute. So the volumetric flow rate for this fuel air mixture is 15.5 liter per minute. And the volume fraction of butane is 2.5%. So the volume fraction of butane would basically mean the fraction of the volume of fuel or volume of butane divided by the total volume of the fuel air mixture, right? So this is 2.5%. Okay. Now, here we are being told that the laminar flame speed in terms of centimeter per second, it can be estimated using this correlation, where if you write down the correlation as 34 minus 139 times 3 minus 1 whole square, and this is going to be in centimeter per second. And here, of course, phi is the equivalence ratio. So we have to calculate what the equivalence ratio is, or if you know the equivalence ratio, then by plugging it into this equation, we can very easily calculate what the laminar flame speed is going to be. Okay, so this is going to tell us the laminar flame speed. Now, for this mixture that we have been provided with, this mixture of which has a volumetric fraction of butane of 2.5%, we need to determine the velocity and the direction of flame propagation, right? So basically, the idea is that we have two velocities in opposite directions. One is the unburned gas velocity, U, which can be found out by making use of the volumetric flow rate of the mixture given. And the other velocity is the laminar flame speed, which is going rapidly or which is traveling rapidly towards the unburned mixture. So we'll have to calculate both of these, and then based on whatever dominates, we'll be able to identify the direction of flame propagation and what the net velocity is, right? So that's roughly the idea. So for this calculation, let's start by calculating the unburned gas velocity. That's the simplest one, right? So unburned gas velocity is uh, unburned gas velocity. We're using U for that. So it's simply equal to volumetric flow rate given here divided by the cross-sectional area, right? So of the cylindrical pipe, so pi d squared by 4. We need to convert this volumetric flow rate from liter per minute to meter cube per second, simply because we want the unburned gas velocity to be an SI unit. So we want it to be meter per second as mentioned in this question. So here we'll just do that. So it's 15.5 liter per minute. So this needs to be multiplied by 10 power minus 3 to convert it into meter cube. And then we divide it by 60 to convert it to per second. So now what we have is a quantity which is meter cube per second. Okay. Now this divided by pi d squared by 4. Pi by 4 times d is 5 centimeters. So at 0.05 meter squared. Now when you do the math, the velocity, the unburned gas velocity, U comes out to be 0.1316 meter per second. Okay, so now this is one part of the problem that we needed to know. So this is done. We know the unburned gas velocity. Now what we need to do is simply to calculate the flame speed, the laminar flame speed, which is SR. And for calculating the laminar flame speed, what we need is the equivalence ratio. Okay, so now we will spend some time into figuring out what the equivalence ratio is. All right, so for finding out the equivalence ratio, basically what we need to know is the stoichiometric air-fuel ratio as well as the actual air-fuel ratio, right? Air-fuel ratio or fuel air ratio, depending on how you calculate it, right? We'll do the math in a bit. So for now, let's actually look at the stoichiometric fuel air ratio. Now for butane, right, which is the fuel here, C4H10, for stoichiometric combustion, we know that all the carbon in the fuel has to convert to CO2 and all the hydrogen has to convert to H2O. So we can simply write butane plus some amount of air, O2 plus 3.76 N2, will give us the products of complete combustion, right? Now, for stoichiometric, that is. Now, here the question is, what is the value for or how many moles of air do we need? Now, if you recall, we spoke about using for CXHY, we said the coefficient here, if we call it A is going to be equal to x plus y by 4, right? Which means that the value of A here would be 4 plus 10 by 4 or 6.5. Okay, so using this, we can simply write down the stoichiometric equation, and here it basically becomes C4H10 plus 6.5 times O2 plus 3.76 N2 gives us products. Now we are interested in simply what's happening on the reactant side, and so the stoichiometric fuel air ratio is simply 1 divided by 6.5 times 4.76 moles of air. So this is one part of what we wanted to do. Now, let us go back to the information given to us about the mixture. So we were told about the volume fraction of butane, right? It's 2.5%. So volume fraction of butane simply refers to the number of moles of butane, number of moles of fuel, divided by the number of moles of the fuel air mixture, right? And this basically is 2.5 by 100. Now, when you look at the general formula that we wrote earlier, we basically wrote it as C4H10 plus A times the air, O2 plus 3.76 N2, giving rise to products. Okay. Now, in this particular case, what we have is if we do not know the value of A, right? For in general, we don't know the value of A unless we have been told something about the amount of air being used. What we have now is we can simply make use of this volume fraction, or which is also the fraction in terms of the moles, and we can come up with the value for A by simply making use of the volume fraction given here. So now, using the formula or the chemical reaction equation here, what I can write is the number of moles of fuel is simply 1 there divided by total number of moles. Total number of moles are number of moles of fuel, which is 1 mole of butane, plus the number of moles of air, which is 4.76 times A. So 1 by 1 plus 4.76 times A gives me 2.5% or 2.5 by 100. So here, when you solve it, basically what you end up with is we get the value of A. On solving this equation, we can get the value of A directly. It's just one unknown, one equation. And so we get the value of A to be 8.19. Now, once you know the value of A, then we can calculate the actual fuel air ratio, right? So what we had previously was a stoichiometric one. Now for the actual fuel air ratio, of course, in terms of moles, it'll be 1 mole of fuel. For every mole of fuel, we are taking 4.76 into 8.19. This is the amount of moles of air being utilized. Okay, so that's essentially what we have. Now we have the actual mixture, we have the stoichiometric mixture. So using this, we can simply calculate the equivalence ratio. The equivalence ratio is the actual fuel by air ratio divided by the stoichiometric fuel by air ratio. So which is basically if you divide the actual fuel air ratio to the stoichiometric fuel air ratio, what we'll end up with is simply 6.5 by 8.19. Okay, which means that the equivalence ratio is 0.793. Now, if I know the equivalence ratio, I can simply calculate the laminar flame speed by using this formula. So that's what we will do. So laminar flame speed it will turn out to be 34 minus 139 times 0.793 minus 1 whole square. So here, when you solve for it, we get it as 28.08. Importantly, it's centimeter per second, okay, because that's what was given. So now we'll convert that into meter per second. So it's 0.2808 meter per second. Okay, so now what we have is we have the two speeds, the laminar flame speed, which is the speed of the flame rushing towards the unburned gas mixture, and then the velocity of the unburned gas mixture, which we calculated simply by using the volumetric flow rate. Okay, so by using the volumetric flow rate, we came up with the velocity of the unburned mixture to be 0.1316. Okay, and from the calculation of equivalence ratio, we came up with the value for laminar flame speed to be 0.2808. So the flame speed is higher, which means that the flame will be propagating towards the unburned mixture, or it will be propagating towards the reactants, and it will propagate at a speed which is equal to the difference between these two speeds, right? Because they're in opposite directions. So the difference comes out to be 0.149. So that's simply how we solve the problem. Now here we give a very simplistic correlation for laminar flame speeds. And as we have seen before, the laminar flame speed depends on a lot of parameters. So for different conditions for the same fuel, you may come up with different correlations. And the idea is very simple. There can be different correlations, which can be a function of pressure, equivalence ratio, fuel, as general as we want, right? And these are typically provided in the literature. So we can make use of them and do the simple calculation to figure out where the flame is propagated. All right, with that, we'll end this short class.